Okay, we'll start. Welcome back to the evening session. And this is Jeongseok's second talk in his two-talk series on Quasimaps, wall crossings, and mirror symmetry.
Thank you very much. Yesterday, we've defined yesterday section 2 was stable quasi-maps, epsilon stable quasi-maps, and we've constructed this moduli space of epsilon stable quasi-map with a source curve with genus G and with K marked point, and map has degree D to all such collections. We've defined what this space is, and I missed one statement in this section, which is this moduli space. If there's no confusion, then I will abbreviate this using this simpler notation. Then this space Q epsilon, it carries a nice deformation theory. Called perfect obstruction theory. Which is notion of and Fantecchi. And this actually this perfect obstruction theory itself is this let me write it first and explain later. Maybe we need to derive pullback. Then in the map, F induces this morphism, the cotangent shapes, and maybe we should use cotangent complex here, and we use its dual. Then this is a shift on the universal curve, so we need to take a pushboard. So in the picture, we have this universal curve and this maps to here. And then this complex is defined on here, but it's we take a pullback and we consider this home, then these all things are complex in here, then we should push forward. Or simply like relative obstruction theory. To the free-stable curves is this familiar thing. So, so this is relative obstruction theory, but this is absolute. So actually, this obstruction theory gives some virtual class, which lies in Chow group over some degree virtual of the modular space. And here, VD is the rank of this complex, which is V times determinant of this pullback tangent bundle. degree of V at this part, and plus 1 minus G, and then it's minus 3, and plus K. So this is a Chow degree. So in homology, we need to double it. So the degree, homology degree is twice of this. Okay, then later we'll get integrate as an integration over this class. Okay, then today I want to explain what's the I function and J function, and what's mirror theorem or wall crossing, and what's like difference of mirror theorem, and my personal opinion of difference of mirror theorem and wall crossing. Okay, so to define I function and J function, we need some like variation over this space. So this is called the graph space. So first, let's fix epsilon as before. And a graph space is which now we have this GIT description. This is so notation. I think maybe you can recognize what this notation means. This is a quasi-maps to the product space. And here now we should use, this is already, like we have this GIT description, and we have this canonical description, this ID or 1. Then because in this case, homology equivariant Picard group. So just one makes sense of degree, or maybe in this case even this is isomorphic to second homology of P1. Okay, let me briefly explain what this means. This stability means actually already this notation already contains what stability means, but I want to rewrite what this means. Here, a quasi-map, as we've discussed, this is the data of these maps. Then the action on G is trivial on here and C star trivial on here. This is decomposed into this thing. And let me denote these two are this way, like one cross F2. Then this is infinity stable means first of all before omega k, and one pullback over is our line bundle G. And here we tensor by epsilon, and here to pullback and line bundle determined by ID on C2, and we portion now this by group C star. And actually, we should take some infinity, but in this case, 3 is enough. the condition, first condition is this is ample. And we also need a length condition. Yeah, the epsilon of epsilon times length of any base point x, length of x is into this divisor. This and plus this number 3 times length of x and f2 inverse of in this case unstable locus is the origin in C2. Right? So this number is less than or equal to 1. If it satisfies these two conditions, then we say this object is stable, and we collect to define this graph space. Okay, then let me so simply denote this by just GQ. Okay, then since we have a sister action, another sister action on this step, which is given by this defines sister action on the moduli space, graph space. Right? So then we are only focused on, maybe this is not. I keep this notation for another space. So here, sorry. I've now checked if I think this makes sense, but I can practice. I don't know. Let's leave this. Maybe I've never checked if this is empty or not. But anyway, let's use. Maybe we use this for this graph space with genus 0 and no mark point. Marked point is fine, but I don't know what happens if we consider higher genus. Anyway, let's assume like genus 0 and marked point, no marked point. In this case, we have this action on the graph space, and then the fixed locus. Fixed locus this looks like the source curve looks like we have here P1 and also yeah, this is infinity, which is 1, 0 and 0, 0, 1. We have these 2 points, and also here we may have component, we may have or we may not have But anyway, so we have it here the component C0 or C infinite. It can be marked point or base point, or maybe there may be some curve. Anyway, so here now then on the fixed, because other than 0 and infinity, because it's moving by cis-action, we don't have any. So we only consider normal points, right? So here we don't have any base point, and this F2 maps this like to here. This F2 maps to P1 identically, and F1 in this component P1, this maps constant. This is constant to X, and we call this constant map by this map constant map by evaluation map, and with evaluation map defined from the fixed locus only. Because this is not defined whole space. So we have this map. And on these two components, these two C0 or C infinite, this maps to 0 or infinity in P1. And or maybe that can be base point. So this means you may not have this component attached to 0, and this can be just the point on P1. This can be just base point. Base point means base point to this the stack quotient containing X, which is just double mod G. So yeah, anyway, so the point is the informations of degree. In this case, only we have a topological constraint is degree. Right? The degree is concentrated on either 0 or infinity. And the point, another thing we should keep in mind is on here we can define evaluation map. Let this F0. Sorry. Then before saying that, so and this fixed locus can be decomposed by some D0 and D infinity, whose sum is D. So as I said, the only the degree information is concentrated either 0 or infinity. So this D can be decomposed like D0 and D infinity, attaching these 2 points. So we can decompose this fixed locus with such a label, and let's denote F0 epsilon is a component corresponding to D0 when D0 is D. Okay. And Then, and also we need some another information, and let Z be second covariant cohomology of C star. And here the point should be fine. This be the covariant of C star action. This C star action, we have two C star actions. One is this and one is this, but this is with respect to this action. And then now we define J function. This we need two formal variables, Q and Z. Q is Novikov variable, actually. And we need here, let me denote it first and then later. So log Q and Z are formal variables, so it's fine, but I will explain what H later. And also, yeah, this is some bad notation because D is some like, it can be some effective class, effective curve class. And Q is again Novikov variable, so it defines some like grouping with respect to this effective classes, group, monoid over effective classes. Anyway, so then now using this evaluation map, actually that is proper, so we can do push forward. And as actually as in the previous case, we have this G graph space also has perfect obstruction theory that induces perfect obstruction theories on this loci, fixed loci, so that we can define virtual cycle here. And here we need the C-star covariant Euler class of normal bundle, virtual normal bundle. So perfect obstruction theory is on in the graph space. If we restrict it to the fixed locus, then one fixed part gives obstruction theory of this, and moving part gives normal bundle. So this information comes from that. And so this is definition of J function. This is virtual normal bundle of our fixed locus into graph space. So yeah, so because now, we have this. We have this fixed locus inside the QG epsilon. Okay, then one remark is this is only some part of a localization formula. So this class is actually, so after push forward, this is, yes. Sorry, yeah, sorry. This is some H, this class of second cohomology class of X. So also we have Novikov variable as much as rank over this. So this is like some like all the summation of some corresponding element. So this actually, if we consider this as a formal variable, so this denotes just some formal element inside the second cohomology. Thank you. And I think maybe even when I write this way, I think you may understand what this fixed component is, because yeah, this is labeled by this. When t0 is infinity, that's our f0. So I actually this is not good notation. Yeah, this sorry. So we have this formula. So so this to define J function, we only consider some like one factor of this or this decomposition of this virtual cycle of graph space. Okay. Then when we say J function of x, that means J infinity x, and I function of x, that is J0 plus. Okay. Then I think I'm ready to explain little theorem is. Although this is not some important assume, but let's assume our x is either Fano or labial, because in this case, this is not important, but in this case, mirror map is explicit. So I will explain what that is. So in 0 plus case, so let's consider this part in 0 plus case. So that is d to the d and evaluation push forward. And here we consider 0 plus. And I think maybe like we need, because this graph space depends on D, so we collect all such things. So I think maybe some subscript or upper script of D should be here. Sorry for confusing notation. Anyway, then we only consider this part, like ignoring this part. Then let's expand this. Anyway, so first of all, so this evaluation map push it forward to x. So this part taking values in cohomology of x, and also we have some extra formal variables q. So it's actually q series, and we also need the z. And in this case, it's like 1 over. So in this is actually a rational function in Z, but sometimes we expand it or not. So now let's expand it, this rational function in G into that 1 over Z things. So then we get, after expand, we get this. This is possible because it's Fano or Calabial. So otherwise, some like positive factor of Z can appear. Then this I0Q is an element in Novikov ring, and this is a unit. Novikov. So so now then zero mirror conjecture is now actually this is not anymore conjecture, but then the compare region of J and I. And yeah, the Q is called mirror map, is defined to be this log Q. Q is log Q plus plus this one. So in this case, I1 it doesn't depend on Z, but it may have a cohomological. So actually, this lies in second cohomology class of X with the Novikov variable. So to be more precise, so yeah. Anyway, so this is some cohomology class, although they are not. So this mirror transformation is not just a transformation of Novikov variables. It's actually cohomology. The mirror transformation is cohomology transformation. Then the earlier proof of Kibenthal is we only considered, if we consider the image of H, the pullback of this thing. This is a subring of this. If we consider only the image of the cohomology of P4, then sorry, I should have said maybe from this point, let's say X is quintic. And in this case, we can compute this explicit way. So it's not so difficult. I can tell the region in one word. This is this hypergeometric series. And H is a hyperplane class. I is this in this case, because if we investigate, I mean, this is in general phenomena. If epsilon is 0 plus, then this C infinity and C0 cannot appear. So we only have base point at either 0 or infinity. So that means we can compute maybe some like shift cohomology on P1. That is because any vector bundle on P1 is decomposed, and the vector bundle is the line bundle is maybe only determined by degree. Anyway, so because we don't have another component, we only have base pointers infinity and 0. So, but we are the only component we are interested in is every base point lies in 0. So the computation of this is not so difficult. Okay. So and finally, an event has proof of a mirror theorem. For this case, quintic, for it is about this, which means we use state space like image over P4. Because in the proof, the reason why we need this is in the proof, because we want to use this total section on P4. Yeah. And this mirror theorem actually works for any complete intersection in genus zero case, complete intersection of the homogeneous space. Okay, actually, yesterday I forgot to say something. So in the equation of this two different ways of writing Yukawa coupling. So that was somehow the expected question, but anyway, I forgot to say that. On the left-hand side, we have z variable, and left-hand side, we don't have z variable. But this is because the z has some homogeneous degree. So when we like the meaning we see like this part is only maybe on the second, I mean the H4 class of this J function. So when we do pair, then anyway, so the z variables are gone. So anyway, so right-hand side also doesn't depend on that. Okay, so yeah, so then what I mean, the meaning of maybe mirror theorem, one important meaning of mirror theorem is, so this can really have to extract these numbers through mirrors. So this is now I, and then I is explicit very much. And mirror map is also explicit because like we expanded this to get I0 and I1. So everything is explicit, so that we get ND. Okay, we have a question.
Hello. Yeah, can I? So the fixed locus in the picture, is it stable, or how do you check that it's stable?
So we are considering only stable object.
So okay, yeah. I mean, is it stable? I mean, there are only two marking. Right? You need three.
No, because for instance, like this. Now this has this whole part is of three of such on this specific component. So anyway, because of this vector, we don't really need to worry about the mark and the special point on here.
Okay. Yeah. So, thanks.
Okay, then yes. So yeah. And I want to advertise Jeongseok and Form 6 work. They somehow generalize this mirror theorem to use 4 cohomology over X, and also they consider any genus. So I want to explain what this another word crossing formula is. So yes, word crossing formula is okay. let's return our this space. Forget about graph space now. Then this space has k many marked points. So for each, if we fix I between 1 to k, we have evaluation map. This, but because the pre-stability condition says the marked point is not base point, so this actually vectors through here. So we have really evaluation map in X. This is because pre-stability condition. Also, for each object in Q epsilon, we can assign a line of cotangent bundle of C at point Pi. We have this line, complex line for each element, and then this forming a line bundle. Let's denote this Ti star UR, and this we have this line bundle on our modular space Q epsilon. Then let's denote by psi this first chunkless of this line bundle. So this is the second cohomology class of our modular space. Then for each cohomology class of X now, then we can define such invariant using Brocken notation. This integration over virtual cycle we defined. We need cup product. Pullback of this cohomology class alpha I and psi I. So these are all cohomology class on Q epsilon. So we can maybe integrate over this homology class. Then this is AI, the power of and now we are ready to define some genus G potential function of X. So now let the formal variable T psi, which is T1 psi, just scalar. And if all like this Tn's are formal variable of cohomology of X, then using this variable, we can define genus G potential function. Now this is summation of all E and K to the D over K factorial. Here we need the invariant E psi 1 E psi K. Here, we may need some suffix here as GKD, and maybe our target space X and stability epsilon. And here, GKD and X epsilon. So we collect all such invariant, and then to define genus G potential function. Okay, then let's assume with some complete intersection in projective space N. And we have this theorem. You know the Jeongseok's theorem is either Q to the 2G minus 2. And here we have this is Kronecker delta. So this vector is only need in genus 1 case because it's maybe called dilaton shift. And this is Euler topological Euler characteristic over X. And we need the 24 here. And here log I0 2. Anyway, so we need this correction in genus 1 case. And sorry, this is correction for all case. And this is only for genus 1 case. And here we need of G 0 plus QT. So this now potential function is equivalent to infinite potential function after mirror transformation. Now 0 Q A 1 Q. This is really now a higher genus mirror symmetric statement. So K, and later, actually, recently, this is proven for general X, it's proven by Yang Zhou. Anyway, the earlier proof of Jeongseok is he used some geometric structure. So, like on P1, we have between the stability condition on left and right on the wall. We consider this thing, then we really have such morphism like this. We have this only projective space case. So we consider complete intersection, then we have this morphism. Using this morphism, he investigate obstruction theory very well. So anyway, this proof is really geometric. So this can cover, no torus localization. So this is really hold for all cohomology, and also this is statement of a higher genus things. And one remark is this really help to compute higher genus kinetic invariant, Gromov-Witten invariant. The strategy is one is wall crossing formula. So this connects to quasi-map invariant to Gromov-Witten invariant. And so if we can compute quasi-map invariant, 0 plus quasi-map invariant, then using this wall crossing formula, we can obtain chromophaeton invariant of kinting. And the computation of a quasi-map invariant is some, like we compare quasi-map invariant and LG Landau Ginzburg quasi-map on P4. That is more computable. I'm thinking maybe David will talk more about this Landau Ginzburg, or maybe FGR. I mean, I don't know. So GLSM, like counting things. Thank you very much. Yeah, I didn't say much, but the crucial idea is localization of the total section on the target space P4. This section is not like, it's somehow like the action on the source curve, source P1. But if we use this total section on the target space, then we can decompose its fixed locus, and in the fixed locus, I mean, this fixed locus of this is point, right? And many of the quasi-maps and stable maps to fixed point here, they must have degree 0, right? In the quasi-map case, degree 0 is nothing but a stable map. So the only difference occurs maybe this the connecting P1, connecting to fixed point, and some like we can investigate what's happening in such. I mean, anyway, so this is localization.